Tork'un bir kısmı da buraya gidecek. Yani bunu buraya da bağlayabilirdiniz. Herhangi bir şey yok diye düşünüyorum. Bu da mı ödevden? Evet, anladım. Okay. Hazır mısınız? Okay. So let us here say that. Let us say that g of s, h of s is given by the following quantities: s minus z1. Let us say that there is 1, 0, s minus p, and 3 poles: s minus p2, s minus p3. Okay. So let us say that g of s, h of s is given in this form. Okay. In that case, I will try to look at what is necessary for s to satisfy this equation. Okay. What is necessary for s to satisfy this equation? G of s, h of s is equal to -1. In that case, I will first mark where these poles and zeros are. Let me say that there is a pole here. This is P1, P2, and I have P3 here. Okay? And I have, let me say, Z1 given here. Okay? So now let me try to check what is necessary for a test point S to satisfy this equation. Okay? For it to satisfy that equation, I need to satisfy the magnitude condition and the angle condition here. Okay? This is the magnitude condition and the angle condition. So now I will look at what those vectors are. S minus. So here I can here write this vector as S minus P3. This is the vector S minus P3. Okay? So here I can write this is S minus Z1 vector, okay? And this is S minus P2 vector, and this is S minus P1 vector, okay? So then magnitude condition is related to the magnitudes of these vectors, and the angle condition is related to the angles of these vectors. So here, let me here put some labels. Let me say that this is the point A, B, C, D, and let me say that this is the point E. Okay? I know that the magnitude condition is going to be in the following way. It is K times the magnitude of S minus Z1. S minus Z1 is going to be the distance AB. Okay? Divided by the magnitudes of S minus Pj vectors. These are going to be AB and, these are going to be AD, and I have AC, and I have AE. Okay? This should be equal to 1. For the magnitude condition to be satisfied, I need this equation to be satisfied for some positive K. Okay? What about for the angle condition to be satisfied? What is necessary? So I will call this angle as theta 1, and let me say that this angle is theta 2, and let me say this angle is theta 3. Okay? And then I will define this angle as phi 1. Okay? Now let me write the angle condition. And in this case, it is going to be the angle of the zero vector, S minus Z1. It is phi 1 minus angles of the poles here, theta 1, theta 2, and theta 3 should be equal to plus minus 2k plus 1, 180 degrees. Okay? for an S point to satisfy this equation, or for an S point to be inside a root locus, we need to satisfy these equalities, okay? For an S point, for a test point to satisfy this equation, or to be inside the root locus, then I need to satisfy these equations for some positive k. So here, in general, we talk about the following. It is actually, what is important here is the angle condition. If a single point S, if it satisfies this angle condition, then we can always satisfy the magnitude condition by choosing a suitable positive k. If we can satisfy the angle condition, if an S point satisfies the angle condition, then we can always select a positive k, which would satisfy the magnitude condition. In that case, I would just calculate this ratio. If this is 1 over 3, then I can choose my k to be 3 to satisfy this equation. Okay? So what is going to be important for us here is the angle condition. If an S point satisfies this angle condition, then the magnitude condition could always be satisfied by choosing a suitable k value. So now we're going to start our complicated example. Yes.
Diğer kenarlar, yani magnitude'lar ve açılar verilirse biz A noktasının hem açısından uzunluğunu bulabiliriz anlamında.
Yok, hayır. So suppose that you have an S point, okay? This S point to satisfy the equation g of s h of s is equal to -1. This point should satisfy both the angle condition and the magnitude condition for satisfying this equation. Okay? If I'm given an S point, and if this S point satisfies the angle condition, then suppose that this point satisfies this angle condition. What is the angle condition? Angle condition is this condition. If it satisfies the angle condition, then we can always calculate these distances, okay? And we can substitute them, and then we can find the k value for which this equality is actually satisfied. So if the angle condition is satisfied, then I can always calculate these distances. So let me say that I have this quantity here. So suppose that I have a pole 1 here, pole 2 here, and pole 3 and pole 4 here. Suppose that there is an S point here. If this S point satisfies the angle condition, what does it mean? It means something about these angles. Okay? So this is theta 1, this is theta 2, this is theta 3, and this is theta 4. The angle condition for this S point is minus theta 1, minus theta 2, minus theta 3, minus theta 4 is plus minus 2k plus 1, 180 degrees. If this equation is satisfied, then I can always look at the magnitude condition, and I can write k times these distances is A, B, C, D, E. These distances are, I have AB, AC, AD, and AE here. These distances should satisfy equality 1. So if this condition is satisfied, I can always find the k by calculating these distances, and multiplication of these distances will give me the required k value to satisfy this equation. Okay? So it is this condition which is important. If this is satisfied, then the magnitude condition is not really that difficult to satisfy. Yes?
How do you make sure that angle condition is satisfied for at least one S and K?
In general, we will see that it is going to be satisfied for at least one S value. We will be able to find those. Or even on the real axis, there will be points satisfying the angle condition. Okay? So now let us look at our example. I have a k here. It is s plus 1, s plus 2, s plus 3, and s plus 4. And I have a unity feedback system given like this. We need to draw the root locus. Draw root locus, meaning the closed loop trajectories for k going from 0 to infinity. We have to draw root locus when k changes between 0 and infinity. Okay. So here let us look at the equation. So I have here the open loop transfer function, g of s, h of s, in this case is k times s, and I have these quantities, s plus 3, s plus 4. And I can also write the condition d of s plus k n of s is equal to 0. This is the characteristic polynomial. Okay? So this is k times n of s over d of s. And my characteristic polynomial is 1 plus k, this thing. Okay? So I have 1 plus g of s, h of s is equal to 0, but it gives me just this characteristic polynomial. Okay? And this thing is s plus 1, s plus 2, s plus 3, s plus 4 plus ks is equal to 0. Okay? So now we would like to draw the root locus for this system. The first thing that we are going to actually determine is where are the open loop poles and open loop zeros. This is my open loop transfer function. Okay? This is my open loop transfer function. And I would like to look at the open loop poles and open loop zeros. So if I look at open loop poles, where are they? Open loop poles are the poles of this transfer function. They are at s equals to minus 1, minus 2, minus 3, and minus 4. Okay? And open loop zeros, where are they? There is only one. It is at s equals to 0. Okay? So now, when we learn about drawing a root locus, we're going to learn some rules. The first 4 rules are the most important rules, and when you learn about them, you're going to be able to draw any root locus that you like, okay, for an arbitrary number of open loop poles and zeros. The coming rules, there are 5 and 6 rules. They're going to give us some details about the root locus. So now let us try to learn about these first four rules. The first rule is related to the number of branches or trajectories. Number of branches or trajectories. How many closed loop poles does this system have? How many closed loop poles does this system have? Its characteristic polynomial is given by this. For each k value, how many roots do we have for this system? 4. So in this case, we have 4 trajectories. Okay? This is the number of trajectories that we have to draw. For this example, I have k over s plus 2. Okay? For this example, I had this, and the characteristic polynomial was s squared plus 2s plus k. Okay? For this example, we have drawn 2 trajectories. One of the trajectories you can think about like this, the other one you can think about like that. Okay? We have drawn in total 2 trajectories, 2 closed loop pole trajectories. Okay? And for this example, I need to draw 4 trajectories. Okay? Because we have 4 closed loop poles, and that is why we have to draw 4 trajectories. Let us try to look at the rule 2. The rule 2 is related to start and end points. Start and end points. So by the start of a root locus, what we mean is when k is equal to 0. Okay? This is called the start point of the root locus. And when k goes to infinity, this is called the end of the root locus. Okay? We started from k is equal to 0 here, and we ended up at k going to infinity. Okay? So here there will be a similar thing. Let us first look at the start point of the root locus. This is the equation that I need to satisfy. So what happens when k is equal to 0? When k is equal to 0, I have this term disappearing. Okay? And where are the roots when at k is equal to 0? Where are the roots of this polynomial when k is equal to 0? They are at s equals to -1, -2, -3, and -4. But what are these numbers? These are the open loop poles. So the root locus starts from open loop poles. Okay? So here, root locus starts from open loop poles. For zeros, we're going to try to do a similar thing. When k goes to infinity, okay? When k goes to infinity, the other terms will be unimportant. Okay? When k goes to infinity, as a result, we need to have s equals to 0. Okay? So that actually tells us the following. Root locus ends at s equals to 0, and s equals to 0 is an open loop 0. Okay? Open loop zeros. So here let us try to understand this a little bit more. We know that this equation is nothing but g of s, h of s is equal to -1. Okay? And it is the same equation that I derived this equation from. And g of s, h of s is given by this quantity. Okay? I have k, s, divided by s plus 1, s plus 2, s plus 3, and s plus 4. This is equal to -1. I'm trying to solve this equation there. Okay? And now let us try to understand how we could satisfy this equation. When k is equal to 0, I need to multiply 0 with a number or with something so that the result should be -1. When k is equal to 0, I need to multiply 0 with a number or something such that the result is -1. What should be that number that I'm multiplying here? If I multiply with 0 any finite number, the result would be 0. It would not be -1. That means that I need to multiply 0 with infinity to get -1. The only way that this equation can be satisfied is for me to multiply 0 with infinity so that I can satisfy the equation. Okay? And when do you think this ratio is infinite? It is infinite at s equals to -1, -2, -3, and -4. Okay? These are the start points of the root locus. Okay? And what happens when k becomes infinite? So now let k go to infinity. Okay? What should I multiply infinity with to get the result -1? The only thing that I can multiply infinity with and get the result -1 is that this number should be equal to 0. Okay? So we see that at k going to infinity, s should be equal to 0. Okay? But this number can be equal to 0 in other ways as well. This number is not only 0 when s equals to 0. It can be 0 at some other times as well. For example, what happens when you let s go to infinity here in this ratio? Okay? So we see here that when s goes to infinity, this ratio would also become 0. Okay? That actually means that root locus ends either at open loop zeros or it ends when s goes to infinity. Okay? So here, come back here. Here I had two open loop poles. Two open loop poles, and how many open loop zeros did we have? How many open loop zeros did we have? No zeros. So where is the root locus going to go? It is going such that s becomes larger and larger. Okay? So s becomes infinite at the end of the root locus. So here we see that there are 4 start points. We had 4 trajectories and we had 4 start points here. Okay? But there is only one open loop zero. It is going to be one of the end points. Okay? So four trajectories, one of them is going to end up at this end point. Okay? Where are the rest of them going to go? They are going to go to infinity. Alright? So only one of the trajectories starting from one of these points will converge to the open loop zero. The other 3, they are going to converge, or they are going to diverge away to infinity. So now let us try to look at the complex plane. So I have real of s, imaginary of s. We had 4 trajectories, and these 4 trajectories, they are going to start at -1, -2, -3, and -4. Okay? And there is an open loop zero here given like this. Okay? So now, when we look at the start and end points, there will be 4 trajectories on this figure, and one of the trajectories is going to converge to this open loop zero, and the other 3, they are going to diverge away to infinity in some direction. Okay? Currently, I don't know how they are going to diverge to infinity, but we know that 3 of them are going to diverge to infinity, and one of them is going to converge to this zero. Okay? Here, that is what happened. I had 2 open loop poles and 2 trajectories. So these trajectories started from here. I didn't have any open loop zero. As a result, both of the trajectories diverged to infinity. Okay? That is what happened. That is how a root locus ends when it doesn't have a zero to converge to. So now let us look at rule 3. Rule 3 is root locus on real axis. Root locus on the real axis. Okay? So here is the time to use our angle condition. Let us say that I have a point here. Okay? I will check the real axis points if they satisfy the angle condition or not. Okay? Let me try to write the angle condition for this quantity. It is this equation, and the angle condition is the following: angle of s minus angle of s plus 1 minus angle of s plus 2 and s plus 4 is equal to plus minus 2k plus 180 degrees. Okay? So now here, let me try to check the angle condition for a point here. Okay? Let me say that this is my S point. Okay? So here I'm looking at those vectors. The vector S is looking like this. The vector s plus 1 is looking like this. Vector s plus 2 is looking like this, etc. Okay? So what are these angles for an s value here? For an s value here, what are these angles? They are all 0, 0, minus 0, minus 0. Okay? So the result is 0 here. Okay? Can you find me an integer k for which 0 is equal to plus minus 2k plus 180 degrees equality would be satisfied? Can you find a small small k, which is an integer, to satisfy this equation? You cannot. The left-hand side is always 0, and for none of these k values, this angle on the right can be equal to 0. That means that this part of the real axis cannot be included in the root locus. Okay? So what about this part of the real axis? Okay? Let me try to check that. Okay? So here, in this case, these vectors are not here anymore. Okay? I can actually try to draw them like this. This is my S vector. Okay? S is here. This is my S. And S plus 1 is like this. S plus 2 is like this. Plus 3 and plus 4, they are like that. Okay?
Hocam küçük k pozitif mi olmak zorunda?
Efendim?
Küçük k pozitif.
Integer. Pozitif olmak zorunda değil. Yani negatif de olabilir ama integer olmak zorunda. Okay? So here now let us try to look at this case. If my S is here in this interval, okay? Then what can you say about the angle of this S? What is the angle? This angle. This is 180 minus, what is S plus 1 angle? This is 0, and all of the others are 0, okay? Now, can you find me a small k value for which you can satisfy this equality? Yes, k is equal to 0 would satisfy this equality. Okay? That actually means that any point in this part of the real axis will be included in the root locus. Okay? Any point on this axis would satisfy the angle condition, and for some k value, this part of the real axis would be included in the root locus. So now let me look at the other interval. So let me try to look at this. Suppose that I check a point in this interval. In that case, the vectors are like this. So this is my S, S plus 1, S plus 2, S plus 3, S plus 4. Do you think in this case you would be able to satisfy that equality? So here, this thing is going to be 180 minus 180. They are going to cancel each other. The others would be equal to 0. So the left-hand side will be 0. You won't be able to satisfy the equality. Okay? So this part will not be included in the root locus. And if you continue in this manner, you would always see that this part is included and this part is included in the root locus. So this is how you do things by using the angle condition. But instead we could use this equality as well. So let us try to understand the same thing by using this equality. We are always trying to satisfy this equality. So now let me say that S is a positive real number. If S is a positive real number, this is positive. This is positive, 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 positive. All of them are positive when S is positive real. Okay? Can you satisfy this equation by using a positive K? Can you satisfy this equation for the positive real S? That is the condition. It is the same thing as the angle condition that we are trying to check. For a positive real S value, you can never satisfy this equality by using a positive K value. Okay? So what about the case when S is between -1 and 0? When S is real, and if it is between -1 and 0, this number is negative. What about these numbers? For example, if S is in this interval, S is like -0.5. Okay? In that case, this is negative. Positive, 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 positive. By choosing a positive K, can you satisfy this equality? Yes, you can satisfy by choosing a positive K. You can satisfy this equality. For example, we haven't checked in this interval. In this interval, S is like -2.5. Okay? If s is minus 2.5, this is negative, 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 okay? Positive, positive. By choosing a positive k, can you satisfy this equality in that case? Yes, you can actually choose it. Here I have s equals like minus 3.5, okay? In that case I have negative, 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 positive, okay? When you multiply these numbers, you get something positive. By choosing a positive k, you can never satisfy this equality. That is why this part of the real axis is never included. That is what we are checking in angle condition. Okay? Trying to satisfy this equality for some positive k. Okay. And as soon as you use the first three rules, you can actually try to visualize what is going to happen in your root locus. As soon as you put the real axis points, put some arrows. These arrows should get away from the open loop poles and they should go towards open loop zeros. Put some arrows getting away from the open loop poles and going towards the open loop zeros. So get away from the open loop poles, go towards open loop zeros. Okay? Get away from the open loop poles, like this. Get away from the open loop poles. Okay? As soon as you look at this picture, you might try to guess what is going to happen. What is happening is that at k is equal to 0, the four closed loop poles are at these locations. And as I increase k above the value 0, this pole moves towards the right. Okay? It starts moving to the right. Okay? And as I increase k value, this pole at the end is going to end up at this 0. As I increase k from 0 to infinity, this closed loop pole is going to move from the open loop pole to the open loop 0. These two closed loop poles, as I increase k, they are going to approach each other as I increase k. And at some point, they are going to come on top of each other. Afterwards, what should happen? This is what is happening. Okay? After some point, those poles are going to go complex, and they're going to diverge to infinity on some line. Okay? And what about this pole? The last pole is going to, as I increase k from 0, this pole is going to start from this point, and then it's going to diverge away into that direction. Okay? So here, how many poles converges to the 0? How many poles would go to infinity? One pole would converge to this 0, okay? And the other three poles, these two would come here and then they diverge to infinity, and this one would diverge to infinity as well. So three of the poles would diverge to infinity. That is what's happening at the end of the root locus. And only one pole would go to the open loop 0. Okay? So then the question is, how do these poles diverging to infinity would go to infinity? On the real number, there are only two infinities, plus infinity, and minus infinity. But in complex plane, there are infinitely many infinities. We can diverge to infinity on any line. Okay? So that is actually going to be one behavior of the root locus that is called asymptotes. Okay? That is going to be the fourth rule of root locus, and that is going to be the asymptotes. Rule 4. So in rule 4, we are going to be wondering about how the roots are going to infinity. Okay, that is what the asymptotes would mean. we call the lines on which S diverges to infinity as the asymptotes. Okay? So here, if I have n is the number of open loop poles. In this example, n is 4. Okay? Let me say that m is the number of open loop zeros. Okay? And in this example, m is 1. How many asymptotes do I expect? 3 asymptotes. So here, n minus m is the number of asymptotes. Okay? So here, in this example, it is 3. Right? Efendim? Because there are 4 branches, and out of these 4 branches, one of them is going to converge to this open loop 0. So the number of branches is the number of open loop poles. 4 trajectories, one of them is going to go to this open loop 0, the rest should go to infinity. Okay? The difference is going to be the number of asymptotes. So now let us try to look at this equality again. S, and I have S plus 1, S plus 2, S plus 3, and S plus 4. This should be equal to minus 1. And we know that what is important here is the angle condition. And the angle condition tells us that the angle of this thing is going to be plus minus 2k plus 1, 180 degrees. This is my angle condition. Okay? So in this case, I'm going to concentrate on what happens when S is very large. If S is very large, then how can I approximate this ratio if the magnitude of S is very large? Yes? This is S plus 1. How can I approximate this when S is very large? I can just approximate it as S. So here this is S over S to the 4. Okay, so I can actually approximate this whole thing like 1 over S cubed. Okay? So in the general case, I have S to the n here in the denominator, and I have S to the m in the numerator. So when I do this approximation, I would get S to the power n minus m. In the general case, I can approximate it like that. And this angle should be equal to plus minus 2k plus 1, 180 degrees. Okay? So now I can actually write this as minus 3 angle of S is equal to plus minus 2k plus 1, 180 degrees. Okay? So then the angle of S should be the following. Angle of S is plus minus, or here I can write minus plus because of this thing. Like this. 2k plus 1, 180 divided by 3. Okay? In the general case, if I write this, it's going to be looking like this. Plus minus 2k plus 1, 180 degrees divided by n minus m. In the general case, I would just have this equality. Okay? So in general, here, we see that I can actually look at the angle of these asymptotes. Usually, we would call the angle of the first asymptote, we define it as 180 divided by n minus m. This is defined as the angle of the first asymptote. Okay? And in this example, it is going to be 60 degrees. Okay? This is the angle of the first asymptote. And we only define usually the angle between asymptotes. If you look at here two consecutive k values, what is the angle between these numbers that you obtain? It is going to be 360 divided by n minus m. Okay? So the angle of the first asymptote is usually defined as 180 divided by n minus m. And angle between asymptotes is 360 divided by n minus m. So in general, in order to be able to derive the asymptotes, we define also the intersection points of the asymptotes. Unfortunately, we will not be able to derive the formula. I will just give you the general formula for this case. The intersection points of the asymptotes are called sigma 0, and it is given as the summation of the open loop poles minus summation of the open loop zeros divided by n minus m. Okay? We won't be able to derive this formula, but it is also derivable by using the same equation. You can also derive intersection points of the asymptotes given like this. And in this case, if I try to calculate this intersection point, it is going to be the summation of the open loop poles. This is going to be minus 1, minus 2, minus 3, and minus 4. Okay? These are the summation of the open loop poles minus summation of the open loop zeros. This is only 0 divided by the number of asymptotes. It is 3. Okay? And in this case, it is minus 10 over 3 is going to be the intersection point of the asymptotes. For this example, I have 3 asymptotes. The first asymptote is going to have 60-degree angle. So it is going to have a 60-degree angle like this. The next asymptote is going to be 120 degrees apart from this. 60 degrees, 120 degrees apart is going to be 180 degrees of asymptote. And the next asymptote is going to be 120 degrees apart from this. Okay? These are my asymptotes here. So now I can actually complete this root locus. So we see that one of the closed loop poles is going towards there on that asymptote. Okay? The other two, they're going to meet at a single point on the real axis, and then they're going to go to the asymptotes afterwards. Okay? So this is what happens on this root locus. There are 4 closed loop poles. As I increase k, this one moves towards the right. These two would come towards each other, and this one would go to that part. And finally, if I increase k sufficiently large, these two would separate from the real axis, and they would diverge away to infinity on the asymptotes. So here, if I ask you the following question, find me the largest k value for which we will not have any oscillations in the step response. Find me the largest k value on this root locus, the largest k value for which we don't have any oscillations in the step response of the closed loop system. Which point should I concentrate on the root locus? I need to concentrate on this point, because after this point I will start getting complex roots. Okay? So if I increase, I need to find the k value at this point, and for larger k values, I would start getting oscillations in the step response. Okay? This is one important point for which we are going to try to find. And another important point is that find me the range of k values for which the closed loop system is stable. which point or points on the root locus should I concentrate for stability? I need to concentrate on these intersections. So these are going to be the two details that we are going to be concentrating on the root locus. One is this separation point. It is going to be called breakaway point in the root locus theory. And another point that we will concentrate is these points with the intersection with the imaginary axis. But that's going to be all for today. Thank you.